Welcome back, class. Today we are going to explore gas mixtures and look at how having a mixture of gases might change things. So, first of all, let's approach this in terms of the variables that we know about a gas, right? So, when we think about a gas, we think about its pressure, its volume, its temperature, and of course its moles. Now, when we think about a gas, right, in a mixture of gases, now a couple of things that we can say. First of all, we can say that all of the gases are going to be at the same temperature, right? So if I have a mixture of nitrogen and oxygen, right, and they're at some temperature, right, the nitrogen's not a different temperature than the oxygen, right? And the same volume, right? So we can think about it because they mix homogeneously, right? Gases always mix homogeneously, and they're going to all spread out to occupy the entire container. So even with a mixture of gases, we say that each gas is occupying that entire volume. So the volume and the temperature are essentially going to be the same for every gas in a mixture of gases. Now, the one thing that does change is the pressure. So the pressure depends on the moles of gas. So let's say we have a mixture of gas and it's 50% of the moles are oxygen, 50% of the moles are nitrogen. Then that means 50% of the pressure is going to come from oxygen and 50% of the pressure is going to come from nitrogen, because if we think about it, if we have, equal moles of gas, then each gas is going to have equal numbers of collisions, it's going to create equal amount of pressure. And so the pressure created will depend upon the moles of that gas that are present, right? So if I have 60% of a gas and 40% of another, then 60% of the pressure is going to come from that one gas and 40% of the pressure from another. So in terms of the pressure, the gases behave independently. So we can come up with an equation that relates the total pressure of a gas sample to the partial pressures of the individual gases. So the partial pressure is the pressure of a single gas in a mixture of gases. And of course, if you add up all the partial pressures, they will equal the total pressure. And this is what's known as Dalton's law of partial pressures. Now, a couple of things to think about is each one of these individual pressures could be calculated using the ideal gas law, right? So the pressure of gas A is equal to, so remember PV equals nRT over V, right? It would be moles of A RT over V. Remembering that V and T are going to be the same for every gas. So it's really just as the moles change, the pressure changes. And of course here, the total pressure can also be solved using the ideal gas law if we wanted to do that. We would just use the total moles. So the total pressure would equal the total moles times RT over V. Okay, so let's put Dalton's law of partial pressure to work. So let's say we have a gas mixture and the total pressure is 745 millimeters of mercury. It's a mixture that contains CO2 at 125 millimeters of mercury, contains argon at 214, contains O2 at 187, and contains helium. And we want to know what is the partial pressure of helium in the mixture? Okay. Now, following that, we'll address the second part of this question, which is how much helium in terms of mass would be in a 12-liter sample of this gas at 273 Kelvin. So, let's solve for the partial pressure of helium. So, first of all, we can know that the total pressure, right, is going to be equal to the pressure of CO2 plus the pressure of argon plus the pressure of O2 plus the pressure of helium. And so since we want to solve for the pressure of helium, right, the pressure of helium would be equal to the total pressure minus the pressure of CO2 plus the pressure of argon plus the pressure of O2. So if we start plugging in numbers, we have a total pressure of 745 millimeters of mercury minus the pressure of CO2, which is 125 millimeters of mercury, plus argon, which is 214 millimeters of mercury, plus O2, which is 187 millimeters of mercury. So if I do that, now if I add all these up, I get 523 millimeters of mercury. So 745 minus 523, the partial pressure of helium equals 222 millimeters of mercury. Okay, so we solve for the partial pressure of helium here. Now, the second question says, what mass of helium is present in 12 liters of gas at 273 Kelvin? So this is a little tricky because the temptation is to want to try to figure out the mass. But remember, in a lot of the things we do, right, everything is based on moles. And we know how to get mass once we know moles. So oftentimes the approach is to figure out the moles and then we can get grams. And that's exactly what we have to do here. Remembering that this partial pressure, we can use the partial pressure to figure out the moles of any particular gas using the ideal gas law. So if I solve the ideal gas law for the moles of helium, so it's going to equal the pressure of helium times the volume over RT. Now remember, I have to have the pressure in atmospheres. So I got to convert my 222 here. So remember, 760 millimeters of mercury per 1 ATM means this is equivalent to 0.292 ATM. So let's go ahead and put this in. We have 0.292 atm times a volume of 12.0 liters. Our R equals 0.08206 liter atmospheres mole Kelvin. And our temperature was 273 Kelvin. So if I do that, I get an N moles of helium equals 0.156 moles of helium. Now that I know moles, now I can get to mass, right? So if I take my 0.156 moles of helium, and I use the molar mass, right? 4.003 grams of helium per mole, I get 0.626 grams of helium. So, hopefully this problem shows how we can start putting these pieces together, right? We can utilize the ideal gas, utilize Dalton's law of partial pressure to find the pressure of an individual gas. Then we can use the ideal gas law to figure out some missing quantity about that, some missing property of that gas. In this case, how many moles of that gas are in there. And, you know, then we can figure out grams for moles. But we can start to put these equations together. Now, since the pressure is related to the moles, right? Sometimes instead of knowing individual pressures, we work with what are called mole fractions, right? And so mole fractions are just what fraction of the moles are coming from a particular gas. So it is the individual moles over the total moles. And that's going to be related to the ratio of pressures, right? So if we know that the pressure of gas A over the total pressure is the same as the moles of A over the total pressure, so again, if 60% of the moles are coming from gas A, then 60% of the pressure will come from gas A. Right? And so, if I want to calculate the individual pressure, it's going to be my, what we call the mole fraction times the total pressure. And we abbreviate mole fraction using this kind of script A. It's the Greek letter chi. So eventually we see that the individual partial pressure is equal to the mole fraction of that gas times the total pressure. That's another way that we can get to it. So, in this particular problem, we're told that we have a mixture of gas that's 1.25 grams nitrogen, 0.85 grams oxygen in a 1.55 liter container at 291 Kelvin. We want to know the mole fractions and the partial pressures of each gas. And finally, they tell us that the total pressure is equal to 1.1 atmospheres. Okay. So, the first thing first, right? We can't really do this problem using Dalton's law, at least not very easily, right? We don't have the right information. We don't have individual pressures, at least not in the sense that we could get them. So, perhaps that's not the right approach. But we do have information that allow us to know the individual moles of gas. So let's look at each of these masses of gas, and of course we can convert these into moles, right? So I know that I have 1.25 grams of N2, and I can convert that into moles, because 1 mole of N2 equals 28.02 grams of N2. And so if I do that math, I get 0.03 significant figures, 446 moles of N2. If I do the same thing for oxygen, I have 0.85 grams of O2, 1 mole of O2, 32.00 grams of O2 equals 0.02. Now, I only got 2 significant figures here, so I should probably have to cut it off there. So that rounds to 27 moles of O2. Now, just a couple things to think about here. So now that I have these moles, I could use the ideal gas law to solve for the pressure of each gas, right? Because I do know the volume and I know the temperature, and those are going to be constant. And so I could solve and find the pressure of each gas from the ideal gas law. But that's not necessarily the most expedient way to do it. Right? We'd much rather, or a little bit more straightforward, to work with the mole fractions. And so I have moles, I have moles. So first thing I want to figure out is the total moles. Okay? So the total moles is simply 0.0446 moles N2 plus 0.027 moles O2 equals 0.0. Now I can go out 3 decimal places based on my addition, so that's going to round to 0.72 moles for my total moles. And now I can figure out my mole fractions. So my mole fraction of N2 equals 0.0446 moles divided by 0.072 moles, and that equals 0.62. 2 significant figures because of the bottom number. Now the mole fraction of O2 equals 0.027 moles divided by 0.072 moles, and I get 0.38. Now, notice mole fractions, right? They have to add up to 1, right? So if I have all the gases and add up all the mole fractions, they should add up to 1. Now that I know the mole fractions here and here, I can use them to calculate the partial pressures. So the pressure of N2 equals 0.62 times the total pressure, which was 1.10 atm. And again, 2 significant figures. That goes 0.68 atm of N2. My partial pressure of O2 equals 0.38 times 1.10 atm equals 0.42 atm O2. And of course, the sum of these partial pressures, right, should add up to the total pressure, which is 1.1. Now, there may be certain rounding errors, but what we can see here is, the fraction of the moles is going to be directly related to the fraction of the pressure, right? So if I have 62% of the moles, 62% of the pressure is going to come from that, right? And 62% of 1.1, right, is 0.68. That's essentially the calculation that I did. So mole fractions is another sort of useful way that we can work with partial pressures when we have a mixture of gases. All right, so that's about all that we want to talk about with gas mixtures. Next time, I want to look at gas stoichiometry. So again, we're going to revisit what we've done the last couple of chapters. We saw it in chapter 4 for pure materials. We did it in chapter 5 for solutions. And again, we're going to do a little stoichiometry, working with chemical equations where we have information about gases.